Alright, so let's begin. This is section 5.4, and we're going to start looking at graphs. We have been making a unit circle. Let me just kind of do a quick intro to that. We've been doing this, and we start off making quadrantal angles, which means kind of angles that are actually on the axes. And so what we are allowed to do is we're allowed to put this in a certain place. And what we've been doing is we've been going exactly 1 unit away from the origin. But if you go 1 unit away from the origin, do you know exactly the coordinates here? Yeah. 0, -1. Good, good. And then we have trig functions. We have 6 trig functions naming all the different ratios you can possibly make with these 3 numbers. So just kind of quickly do a few here. If I say this right here is my theta, and I say sine of theta is, by definition, y over r, and it's going to be -1 over 1, and 1, there's the r here. Of course, that's the x, and that's the y. Cool. So we've been making these guys. What we also did, and let me change to a different screen. No. Okay, what we also did was we moved off the axes, and we actually went like this. We went like a 1 unit away from the origin. And we have 2 special triangles. We get them from geometry. We get a special triangle. It's a 45, 45, 90 triangle. And if it's set up like this, and this is 1, we actually know the distance here. The distance here is square root of 2 over 2. And the distance here is the square root of 2 over 2. Good there? Then we have another angle, a triangle, that we get from geometry. Is if this is 1, and this is a 30, 60, 90 triangle, that means half the side opposite of the 30 is half of the distance here. And then the side opposite the 60 is the square root of 3 times 1/2, or square root of 3 over 2. So there's our sort of combinations. Based upon these squares, if we go out a certain r value of 1, then we drop an altitude back down to the x-axis, and we can find out that this is actually 45 and this is 45. We actually know the distance here, don't we? This is square root of 2 over 2. The distance here is square root of 2 over 2. So what are my coordinates? Obviously, it's a square root of 2 over 2 over here, and it's a square root of 2 over 2. Do I have everything I need in order to give me all the 6 trig functions? Absolutely. I know my r value, I know my x, and my y. There it is. There's all my trig functions. Ooh, you guys, look at that. Let you guys try this here. Let's go to black screen. Let's see if this is funner. Okay, another one. How about this? How about if I'm 1 unit away, I go over here. It's supposed to be a straight line. And I know this guy to be 120 degrees. Well, I can still drop an altitude, like this. Not drawn to scale here. What's my degree right over here? Not drawn to scale. Looks like a 45. Just trying to confuse you. If that's 60, because it has to be 180, that means this guy has to be 30. And if r is 1, then the side opposite my 30 is? Has a distance of 1/2, right? And the side opposite my 60? Okay, now what's the coordinate here? Perfect. Yeah, it's a -1/2 because you're going to the left of the origin. So it's a -1/2, and it's a positive root 3 over 2. Good there? If that's the case, do I have everything I need in order to give me all the 6 trig functions? So okay, so these 2 triangles are very important. And those of you that went to the upgrade session last time, you guys had fun building these little triangles Okay, I'm not sure if you had fun, but I think you guys had fun building these little triangles onto a paper plate. And because you know the distance here, you were able to find all the coordinates. So we know, and let me just kind of post them up for you here. I know the exact measurement of a 30-degree triangle. I know the exact coordinates here of a 45-degree and a 60-degree. And of course it works the other way too, right? 60 degrees, triangle here, or actually 120 degrees. I also know 135 degrees, because that's 45 away from 180. And then I also know, let's see, 150, right? 150 degrees, because this will give you a leftover of 30. Okay, and again, just real quickly, we can go around this whole entire unit circle. Not fun. Let me try this a different way here. No, don't work. Okay. Okay, so then I can go, anybody real quick here, what's 180 plus 30? 210. 180 plus 45? 225. 180 plus 60? 240. Then of course we know the quadrantal angles, right? We did that one actually earlier, so we know all the ones on the line. Okay, how about let's see, 60 degrees away from 360. That's the way we measure it here. So at this point, once you get to quadrant 4, what we like to measure actually a negative distance away from 0, or a negative angle away from 0. And then we think about what this will be in a positive angle. So technically we're measuring this side, but if we have 60 degrees here, that means this angle is a 300 degree angle. All right, I like the different colors. Okay, so that means if I go this way, you guys tell me, what is this angle going to be? Cool, 315. And then last one, I'll just do it in purple here. What is that angle going to be?
330.
Okay, we're good there. So we just have these and all the ones that are on the line. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 points that I know for sure the coordinates of. Okay, we're good? I think we're able to move on now. What we want to do now is to take it out of this sort of going circles and circles and circles. What I want to do is I want to be able to make a graph. Oh, by the way, real quick here, let's vote here. How many like the white background? And how many like the black background? Which one did you guys see better from? White? Let's take a vote here. Show of hands here. How many say, Mr. H, I like the black background better? 1, 2, 3, 4, 5. All right. How many say I like the white background better, Mr. H? Just George and Erica.
And Jason.
And Jason. That's 3. Are you switching your votes? Now it's 4-4. Is that what it happens? Okay. So let's go for it here. So what we want to do is we actually want to create a graph of the sine and cosine functions. We're going to work with that. In 5.5, then we do all the rest of them. We'd use the tangent, secant, cosecant, and cotangent graphs. But we're going to spend the most of that time with sine and cosine today because we use it quite a bit. We use this one the most. All right, so let me go to another. That's not good. All right, one more little thing to do. Here's what we're gonna do. Again, kind of thinking with me for a little bit. We'll do some practice problems in a little bit here. Just want to see you understanding the concept here. So what I'm gonna do, I'm gonna make two things here. I'm gonna make a little table. This is gonna be my theta, and this is gonna be sine of theta. And we're going to change it up a little bit. We're going to change it into, instead of degrees, we're going to use radians this time. So at 0 radians, you guys tell me what is the sine value?
0. 1, 0.
Sine value is y divided by r, right? So it's 0 over 1 or 0. We're good? So as I move up to here, let's see, this is going to be a pi over 6, and this is a 30-degree triangle. What's the coordinates, anybody? Square 3 over 2, 1/2, and hopefully you found it in your textbook as well. What's the pi over 6? What's the sine value of pi over 6? Sine value is the y coordinate divided by r. In this case, it's 1, so we don't even care about it. Everybody okay with 1/2? This guy here? All right, and this is about 0.5, right? That's exactly 0.5, actually. Okay, let's go a little bit more here. 45-degree angle. 45-degree angle is pi over 4. I know that from last time. Can you guys give me the coordinates? 45s are easy because they're both the same.
√2 over √2.
Awesome. So the sine value is √2 over 2. Anybody know a approximate decimal approximation? 2 decimal places would be fine. 3 decimal places would be better.
Square root of 2 over 2 divided by 1?
Oh no, yeah, divided by 1. We don't really need the 1 because it's just a 1. The question is, why don't we divide by r? Because r is 1, so there's no division happening. Anybody got decimal approximation for √2 divided by 2?
0.707.
Awesome, I like that. Cool. Okay, next one. The 60-degree angle. This is pi over 3. This is going to be 1/2 and square root of 3 over 2. Drawing pi over 3. Let's see, I got square root of 3 over 2, don't I? And anybody have a calculator? What's square root of 3 over 2? 0.86, okay. And then when we get to here, finally the 90-degree angle. What is sine? Let's see, it's 0 sideways, but 1 up.
Oh.
It's 1. Okay, so let me see if we can kind of consider this here. As I go this way now, remember these guys are going to repeat themselves, right? So this angle here is -3 pi over 2. The coordinates is a -1/2, but still at √3 over 2. So it starts to cycle back, doesn't it? It's a repeating now. So that means if I go 3 pi over 4, which would be 135 degrees, what is the answer here? Still positive, right?
2 over 2.
Uh-huh. So approximately that. Again, approximately 0.87 or 86. Okay, just a little more here. They'll connect these. Let's see, and then 5 pi over 6, because that would be the equivalent of 150 degrees. Everybody okay with 1/2 being the answer? Eventually at pi, how about an answer of 0? Then it goes under. Then we're going to deal with the negative values. Here's what I want to do. Instead of being a circle, it goes through a unit circle, this is what I want to do. I want to make it into a graph. And we're going to change this up. We're not going to longer call it theta, because theta actually means sort of like an angle. we're going to usually call it t, or actually we can call it x. That's fine if we call it x. This is the x coordinate, that's the y coordinate. Okay, so let's start off 0. Let's start plotting these points here. So 0 is equal to 0, right? So we got this point here. As we start putting out from here, this is pi over 6. And let's say this is 1 right here. This is 1. Let's make a scale. So tell me if you guys agree here. Pi divided by 6, it's 1/2, right? So it's 0.5 here. As we go further out, I get myself a pi over 4, and that reaches 0.707. Then I go out to pi over 3, and that reaches a it's going a little bit high here. Huh, that is interesting. Sorry, getting used to these interesting pins that don't seem to work very well. Did it again. White screen. Sorry, I changed options here on this. Okay, never mind. Let me just do this. Okay, so let me see if we can do this one. I'm going to blow it up just a little bit here. So 0, 0. Pi over 6 became 0.5. Pi over 4 became a 0.707. Maybe like right there, maybe a little lower. Pi over 3 became a 0.86 or 87, somewhere right here. And then we get ourselves pi over 2. Pi over 2 came to be 1. And let me actually put the marker across here as 1. This is 0.5, that's 1. We good there? Once it heads into quadrant 2, as you guys have it on your sheet of paper, that one is going to be a 2 pi over 3. And it heads back down to a 0.68 or 0.86. It goes down to 3 pi over 4. Now we get ourselves a 0.707. And then 5 pi over 6 gets me 1/2. And then what does pi give me in terms of sign? At 0. So if we start filling this in, so it looks like it's going to happen, look like it's going to go this way.
You have a big class.
Oh yeah. Okay. And then it's going to go down like this, right? Because it's going to go negative territory. And eventually it's going to come back up. I'm going to scale it a little bit so I can see the end here. It's going to go look like this. That is kind of cool. We've just made a graph of y is equal to sine of x. We just made a graph in which all numbers are real. We just planted it on an x and y grid using x and y variables from the unit circle. That's exactly what we're going to work with now. All right, does the sine function, does it stop here? Does it go on forever? Can I go around the unit circle again and get values? Absolutely. Can I go to the negative angles to get values? Absolutely. So I can go like this forever. Okay, so here's my graph right there. Okay, a few questions here. Ready? Anybody? What is my domain? Negative infinity to positive infinity, right? There's no breaks in the graph, not like with the rational functions. What is my range? My range, with this we say it oscillates, right? It goes between two things, right? So it goes from -1 to +1. And so the way we write range in here, because it does touch -1, so how about brackets, -1 to 1. I'll show it in just a bit here. Second one, how about, can you name me all the zeros? This was a tough one here. Name me all the zeros. And so all the zeros are here. That's a 0. Then you go to pi. Then you go to 2 pi. Then can you guys guess what's going to happen here? What is this one right here?
0.
Yeah, but what's the x coordinate right here? Just should be see a pattern, right? 0, pi, 2 pi. Next would be 3 pi. Going the other way, negative pi, and I'm sure this one will have to land where? Negative 2 pi. All right, eventually negative 3 pi. So how do we say, notice this is kind of weird because they're individual pieces, right? They're individual numbers. All right, the way we're going to say it is this right here. It says all the zeros for this is given as, and again, t or x, whatever you like. The book uses t, I can use x. X equals n times pi. And then we got to figure out what n is. N is an integer. Okay, just let that soak in just for a little bit. Does that make sense? If n is any integer whatsoever, or all the integers, my zeros can be found just by multiplying that times pi. Okay, we good there. What do you guys say? Even, odd, or neither? And Mr. H, what's odd? What's even? What is that? That's like 2 weeks ago. All right, here you go. I'll show you an even function. Even function, always think of x squared as being an even function. You have symmetry about the y-axis. The odd function are x cubed. They go like this. They have symmetry about the origin. Any one of those fit the y curve? I think it's an odd function, huh? Because a positive, here, let's go, a positive x positive y also can be mapped to a negative x positive y, right? That's what a definition of a even function is by coordinate definition. And odd function says this: if I have a positive x positive y along my function, I'm also going to have a negative x negative y as well. So do we get that here? Yeah. Positive x positive y. Going back the other way, a negative x then gives me a negative y. Okay, good. We're going to do the exact same thing with the cosine curve. Again, don't have time to illustrate it here, but if we take the cosine curve off the unit circle, and with that unit circle, it looks like this. A little bit different. All right, again, let's quickly go through this here. Real quick here, domain. Negative infinity, positive infinity, everybody agreed? Range. Negative 1 to 1, and what the little special word we say is inclusive, which means it's actually including the endpoints as well. Cool? All right, even, odd, or neither? Hey, this one's an even function, right? Isn't it symmetric about the y-axis? So a positive x positive y would give you a negative x positive y. Cool, all right. And then the zeros are a little bit tougher this time. The zeros are at negative 1 pi over 2, positive pi over 2, 3 pi over 2. Looks like this one's going to be a 5 pi over 2. Hey, this is a little different. Notice the integer values here. 1, then 3, then 5. Slightly different here. There's negative 3 over here, and then eventually we guess it's going to be negative 5 pi over 2. How do we write it? We say x is equal to pi over 2 plus n pi. That's the way the book wants constant. Again, n is an integer. So really it's just pi over 2 removed from just the regular integer cycles of pi. Okay, we do have to memorize this practically. We have to memorize the key and important points of a sine curve and a cosine curve. And here they are in the textbook here. I'll try to find them here. These are on page 519 if you want to jot that down. These are the ones we should memorize. These are the ones we're going to use in order to build our graphs here. So 0, 0 for sine is going to be 0, 0, pi over 2, comma 1, pi 0, 3 pi over 2, negative 1, and 2 pi 0. So you got a high point, a low point, and then you got the intercepts. Going back over here, for cosine, it's a little different. It starts high, and it goes down, and then it comes back up. So the little calculus sort of you'll probably hear, the sine curve has a high and a low, or a hill and a valley. And the cosine curve just has a deep, deep valley. Are we good? Okay, that one you should have a pretty good grasp of. We're going to actually use these in order to do some work here. All right, let's think about transformations before we get to the other stuff. Transformations. So I want us to graph y is equal to sine of x. Then let's graph y is equal to 5 sine of x. Then graph y is equal to 1/5 sine of x. We want to graph from negative pi over 2 to pi over 2. So again, this section is going to be all about graphing. We graph, and we graph some more. And we might make it to the word problem. We'll see. Okay, ready? So it gives us how we're supposed to graph. We're going to go from negative pi over 2 to pi over 2. So let's set that up already here. So the way we graph it, make an x and y coordinate grid, and let's start marking things off. Okay, that'll be pi, so that means that's going to be 2 pi. Going the other way then, that's negative pi over 2. This is going to be negative pi. 3 pi over 2, then eventually get a negative 2 pi on the other side. Okay, also, we kind of know what the sine curve is going to do, right? It's going to go up and down and up and down. All right, so the only thing that's kind of interesting here is this little 5. So do you guys remember how this used to be the stretch, the vertical stretch?
Yeah, so now it's gonna go to 5. Now it's gonna go to 5.
Yep. And so let's go down 5. 1, 2, 3, 4, 5. Okay, now let's start our sine curve. The regular sine curve is going to be 0, 0, right? Then it goes up to 1. Notice what I'm doing is I'm breaking it up into sort of like 4 different pieces. I start at 0. I go up to its highest point. I go back down to 0, then I go to its lowest point, and then I go to 2 pi. Hey, those are the things from the previous slide. Interesting. All right, we can go the other way because we have to graph from negative 2 pi all the way to positive 2 pi. So let's go backwards there. So that means this has to go down, back up to 0, then up to a high point, and then back down to 0. There's my cycle from negative 2 pi to a positive 2 pi, and of course we have to connect all the pieces here, and that should look like this. All right, does it look like a sine curve? I think so. Okay, so now let's think of y is equal to 5 sine of x. All right, the number in front acts as a vertical stretch. So we're going to stretch all these points here. But hold on, if you're at 0, 0, aren't you going to stay at 0, 0? So none of the x coordinates or x intercepts are going to move. They stay in one spot. But this one that was a 1, pi over 2 comma 1, and this one's going to go 5 times higher. Right? So back down to 0. Since this was a negative 1, guess what's going to happen here? It's going to go 5 times lower, and then eventually still gets to 0. So same thing goes the other way here. That'd be negative 5, back up to 0, back up to positive 5, down to 0. And of course, we are going to have to connect the points. Okay, so what's going to happen if I have y is equal to 1/5 sine of x? Yeah, so now starting off 0, 0, right? Now instead of going all the way up to 1, it only goes up 1/5 of the way. Then again, then it's 0, 1/5 the way down, then back to 0. Okay, on the other side, 1/5 of the way down, 0, 1/5 of the way up, 0, and then connect them, and there's my. So really, it's just transformations all over again, but now with these curves. What do sine and cosine let you model is anything that sort of oscillates back and forth. A few things come to mind. How about temperature? Does temperature sort of go up and then come down? Absolutely. If that's the case, every single day we can actually model how the temperature went up and then how it came back down by a sine curve or a cosine curve, whichever one you prefer. Let's see some other stuff here. One that's more repetitive. When I was teaching trigonometry in high school, we did phases of the moon. This was kind of cool. You know how you get a full moon, right? So you got 100% of the moon is showing. Then eventually you get down to 0% of the moon is showing. We were able to build a trig function that can model that forever based upon the day, which I thought was kind of cool. Okay, so that is what happens with that. Let me skip a few. Let me just show you the next one here. What's a negative gonna do? Let's not do that, but let's what's this negative gonna do in front? I'll give you a hint. It starts with re and ends with flexion. Yes, it's reflection about the it's a reflection about the x-axis. So if you have a cosine curve, you're going to now reflect it about the x-axis. What does that look like? Here it is. Here's the original. Y is equal to 2 cosine is blue. And then when you take the negative of it, again, anything that was a positive 2 becomes negative 2. And notice these zeros still stay at the same spot. No moving of zeros. Okay, now let's deal with a little bit of a more complicated matter. Should I? You guys need to graph one, or are you guys okay? Let's graph one, okay. All yours here. Can you graph for me y is equal to 5 cosine of x? So from beginning to end. Okay, let me start as well here. So there's my 4 points there. One go to pi, the other one go to 2 pi. One I'll go into negative 2 pi. And again, I'm going to start out with 5 already because I know it's going to have it's going to go reach up to 5, right? Reach down to negative 5 eventually. Alright, so think about how cosine starts off. Cosine starts off as being high, right? It's the big valley here. Starts off high, goes through 0, hits a low, comes back up to the high. This is the big valley. What's going to happen if we have 5 in front of it? All the times it ever hit 1, now it's going to hit 5, right? Oh, let's go to the negative side as well here. Might as well here. And so, notice so anytime it was at 1, now it goes up to 5. 0 doesn't change. Anytime it's at negative 1, now it goes down to negative 5. Again, 0 doesn't change, and way back up. Okay, let's go the other way here. So 0, it was at negative 1, now it's at negative 5. It's at 0, stays 0. It's at 1, now it becomes positive 5. And there's my final graph. All right, quick show of hands. How many got that one correct before I did the graph? 1, 2, 2. Okay. All right, good for you, good for you. All right, and they do tell us a little something. They actually us to find something. It says find the amplitude and the range of f. So amplitude. What in the world is amplitude? Amplitude is the absolute value of this number here. Amplitude is always positive. So the absolute value of 5 would just be 5. Right? It's the absolute value of that number. So if this was a negative 5, the amplitude would still be a positive 5. So amplitude is the number in front, the absolute value of the number in front. Okay, then we have something called range. And of course, range is the difference between your highest and your lowest, just like we do in statistics. All right, and of course, it's going to be from the highest, which is 5, down to the lowest, which is negative 5, and the difference there, everybody okay with? From negative 5 to positive 5, there's my interval, there's my range. Hey, took down my watch. Okay, let's check one more thing out before we go on to next thing here. Number 3, sketch one cycle of the graphs of y is equal to sine of x and then y is equal to sine of 1/2 x. So now the number that has been changed is the multiplier to x, and this guy is inside the function now. If I'm going to graph it here, so I'm going to go out like this, leave a little space in the positive area. All right, and what should we know? I'm going to write 4 pi over here. We'll find out why in just a bit here. So half of that would be 2 pi, half of that would be pi, half of that would be pi over 2, and that's probably as far as I'm going to. All right, can you guys sketch for me y is equal to sine of x? Can you sketch for me the regular basic sine function? All right, basic sine function. Again, starts off 0, goes up to 1 by the time it gets to pi over 2, goes back down to 0, goes down to -1, back up. So there's one full cycle, because you know after this it's going to start repeating itself. All right, good there? Next, what does this 1/2 do? And the funny thing is, it does exactly opposite what you think it's going to do. Remember when we had the parabola a while back? Remember if we had something like this? Ah, sorry, no, I want the equation here. What did this do to the graph? +4 at the end here.
Shifted it to the left.
Yeah, it shifted it to the left, right? It shifted to the way you think it's going to be its opposite. Well, same thing here now with the multiplier. A multiplier of 1/2, you would think it's going to shrink it down because it's such a small number. But what happens is it actually doubles it. It makes it go out further out. So let me... So 0, 0 still stays because we're not stretching along the... We're stretching along the y-axis this time. And then what we're doing is we're doubling everything for the y value. So if this guy here, or the x value here, this is pi over 0, 2 pi over 0, or 2 pi comma 0. Because of that little 1/2, now this point here has become the point over here. So it just doubled it. This pi over here doubled becomes 2 pi. And then you kind of see where we're going to go with this here. We're going to double pi over 2. That would make it right here. And then let's see. I guess we can do halfway between here and here. Halfway between here and here would be a positive pi over 3. Cool. So I think I connect things now. Boom. 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 Okay. Normally would graph it like that, and it actually tells us only to do one cycle. So we're going to stop right after we do one cycle. Hey. Does this thing ever had a clock in here or no? Or is it just me pretending? I thought it did. I thought this had a clock in it or something. Okay, 6 o'clock, I think it'll be good. Okay, so let's go on to some formulas here. So if I have y is equal to a sine of b times x, here's what I got. Amplitude is a. And the period is an interesting one. Period is 2 pi divided by b, and the b is the multiplier over here. So let's go back just real quickly. Let's use this formula up here. So for this one, if we were going to get the b value for it, if this was sine of bx, the b is a half for us. So if I take 2 pi divided by a half, what am I going to get? have to take the reciprocal 1/2, which is 2. And there's my 4 pi. Hey, notice, look at this. In order for this to start repeating itself, it has to go through a cycle 4 pi long. Okay, we're good there. All right, another way the book wants you to look at it, and again, we're just having fun with these graphs here. Another way to look at it is that these graphs always divide into 4 different pieces. Whether it's sine or cosine, doesn't matter. It's going to have a starting point. It's going to hit a 0. It's going to have a low point somewhere along the line. It's going to hit 0 and then back up to a high point. So this we say period divided by 4, or quarters of a period. Just need to know where you're at. So I'll let you guys try one here by yourself. Can you graph for me 2 cosine of 2x? And again, just 1 period interval. All right, I'm going to start here as well. So I'm going to label things here as, first I'm going to label things as an amplitude, which is 2. Once I know these little pieces, I think I got the rest of it here. So period, let's see, period is 2 pi divided by the b value. So if I get that, tell me if you guys are okay with that. Period should just be pi, right? We are shortening the period by 2. All right, and then we have so that means when I make my graph, I only just need to go this far. That'll get me 1 full cycle, or 1 full interval. So that's kind of important to know the period, because that tells you how far or how big you need to make the graph. Okay, it's the sine. It's a cosine curve. You know, it's going to start high, hit a 0, go low, go back up the hill. So I know I just need to go up 2. I need to go down 2, the little extra left over there. All right, so that's going to be pi over 2. Pi over 4. Notice what I'm doing. I'm breaking up into 4 different pieces. I know what each piece is going to do. First of all, I was going to start off high at 2. So That's what a cosine does. Quarter of the way through, it's going to hit a 0. Then it's going to hit a low point. Halfway through, it's going to start climbing back up and eventually get over to pi. Or get over to 2 as it gets over to pi. Alright, graphing it, connecting the points here. That should be good. Again, quick show of hands. How many got that one right before I got it? 1, 2. Alright, we're still batting 2. All right, let's go from there. Let me just check something. Let's go into look at this here. Don't need to graph it here, but what happens if you have A something in here? Well, we think we know from transformations here. What do you guys think that x minus pi over 2 is going to do? It's going to push it over to the right, pi over 2 units. We're good? And this is called a phase shift. Shifting over to the right here. So notice what the graph is going to look like. Regular old sine curve goes like this. And now this adjusted sine curve for just the compensating for going or starting through with a negative 1/2. We go up 1, over 1, and back to 0. Okay, phase shift, what you do is you do that last. After you've done the amplitude, after you've done the period shift, once you got it all ready pretty much to go, then you do the phase shift last. Then we'll finally put all this together here. So can you graph this for me? And then can you make a phase shift? Right or left? What do you guys say? Yeah, to the right. Pi over 4 units to the right. Cool, all right, let me start it. So it's a cosine curve, no changes to that. So amplitude is 1, period is 2 pi. But we do have a phase shift of pi over 4, and that is going to the right. So since there's no change to the period, I know it does this. That's half there, that's 3 pi over 4, or 3 pi over 2. Okay, let me graph just y is equal to cosine of x. That's the one I want to graph, just to sort of see what we're seeing. And remember, cosine starts off high, hits the 0, low, hits the 0, back up. But what we have is we have a phase shift. Y is equal to cosine of x minus pi over 4. So again, we have a phase shift to the right, and that's exactly what we're going to do. Is we're going to take this blue dot here that we have at 0, 1. We're going to transfer it over halfway to pi over 2, right? Because pi over 4 is halfway here. So again, same thing here. We're going to transfer this pi over 2 dot halfway to pi. The pi halfway over here to 5 pi over 4, if you want to see what that is. And this way halfway, and then this one actually will go off the chart a little bit. That's okay. Even if it goes off the chart a little bit, that's still okay. All right, now we are ready, I think, to put all this stuff together. All right, just the way it looks. Let's take a look at the way it looks here. That's the one thing we gotta see. So let me look at a problem here first before you guys start doing it yourself here. If I were to graph 3 sine, and then notice what we have is we have brackets now. Big humongous brackets, 2, and then you got parentheses of x minus pi over 4. So that means all these things are separated from each other. Notice the amplitude is 3. The period is 2, so this is 2 pi over 2. Shearing point is pi over 4, or if you think about it, it's going to have a phase shift to the right, pi over 4. So as you graph it, again, it should look like this. See if all of this makes sense. Didn't want you to do it, just kind of think with me. It had a pi. So originally it was here. Let's try one here. Let's see if we can go through one together. And of course, I'm going to give you fractions here. It's a toughie. Then we'll do some easy ones together. So, can you find for me my amplitude, my period, and then my phase shift? That's what I want to see. And again, if you're just too much on this one, that's okay. I don't know why they chose this one to do as the first one. This is a whole bunch more complicated than the other ones. Okay, those are waiting for me. Let's try this one together. It is a tough one, and then I think there's 2 easy ones after this here, but let's go for it here. So amplitude is 1/3. Everybody good there? Period is, this is a fun one. It's 2 pi divided by 2 divided by 5. So you got to do a little bit of work there. You got to change it to a multiplication problem here. So how about pi over 2 over 1 times 5 over 2? Hey, Hey, this is kind of nice. 2's cancel. I have a period of 5 pi. So it's going to take a period of 5 pi in order to move. Since this is cosine, we're looking from going from the top to the bottom back to the top. Just the big old valley. All right, let's go for it here. So phase shift, again, negative pi over 6. Notice I put that negative in there. It's not an even number, this 5 pi over this 5 pi, so 5 pi over 2 would be the middle point. All right, let's see. So cosine would do something like this. It's only up 1/3. It's going to hit a 0, quarter of the way up. It's going to go down 1/3, back up to 0, and then up to 1/3. Everybody good there? That'd be y equals to 1/3 cosine of 2 pi, 2/5 x. Now let's add in the phase shift. The phase shift, we can add the little points in. If you would like, you can add the points in. This would be 5 pi over 4. This would be 10 pi over 4. And this would be 15 pi over 4. Okay, now the phase shift. Phase shift just says we're going to have to scoot it back negative pi over 6. So this little black dot has to scoot back. This little dot of 5 pi over 4 has to scoot back. And so we put it like this. Again, you have to sort of know your distances here. You got to think about, okay, what is 5 pi over 4? This is just a little bit beyond pi, right? Pi over 6, is that a whole bunch lower? Yeah, pi over 6, that's a lot lower than 5 pi over 4. So it's going to just move it back a little bit here. And sometimes in the book, they actually make you even find the coordinates. So this one would be pretty easy. What is the coordinates of this first blue dot right here? Well, since it was at 0, we moved it back. Wouldn't that be a negative pi over 6? And would that be okay to make it a 1/3 as well? Because 1/3 came from their amplitude. Okay, the fun one, I'll let you guys find this one here. What is this point here, that last blue point? Can you give me the exact answer for that coordinate? Cool. This would be, let's see, wouldn't this be 5 pi minus pi over 6? Technically. I have to get common denominators, of course. So how about 30 pi over 5, or sorry, 6 minus a pi over 6. Therefore, we get ourselves a 29 pi over 6. That's my x coordinate, and then my y coordinate is 1/3 still. Oof, how many got that one right before I said it? Haha, got you guys all. This is actually pretty cool too, because you can measure, let's see, elasticity of rubber bands. I mean, anything that goes up and down, anything that oscillates, you got yourself a model of behavior for it. Electricity, it oscillates. The reason why electricity works, as it comes in through the outlet in the house, we call it AC current or alternative current. What happens is it's actually spinning back and forth, back and forth, back and forth. And that's what makes that electricity. It's doing that at 60 times per second. That's why we say we live in a 60 hertz. Electronic system. Electric system. Okay, everybody good there? Seeing how to get the exact answers? Let's try just a few for you guys to practice. Okay, no fractions this time. Can you guys graph for me from beginning to end, this guy here? Again, think of reflections, think of amplitude, think of period, phase shift, all that stuff. And let's see, give me at least 2 points with like some detail. Guess maybe I could say it that way. Give me 2 points that give a detail where it should be. All right, sometimes it might take more than one graph, so kind of be mindful of that. Sometimes you have to adjust the settings in the graph when you originally did it. Sometimes you're moving a little bit too far to the left or right, so you have to adjust the rest of the graph. So lots of things here to think through. All right, I'm going to start here as well. So there's my function. Amplitude is a 2. And because it's a negative, we know that there's a reflection about the x-axis. Second, my period is 2 pi over 3. Oh, that's not a good thing. Got some fractions here. And then my phase shift. My phase shift is the opposite of whatever's inside there. There's the multiplier here, so how about a negative pi? Just got to put all that together here. Graphing this, I'm going to go out. So it says only graph one single period. I'm going to graph it at 2 pi over 3. So that means this guy has to be 2 pi over 6, or actually technically pi over 3. Right? That's half of 2 pi over 3. And then if you take half of that, that'd be pi over 6. And if you add those guys together, pi over 6 plus pi over 3, you get pi over 2. That's what we're looking at. All right, let's see, I know I have to go up at least to 2 because of that 2 there. And I know also I have a reflection, so cosine. Cosine starts from the top, goes down, goes up. Because that reflection, I know I'm going to start low now. I'm going to start low, go all the way up like a mountain, come back down. So 0, that was the first quadrant of our function. 0. And now we have to introduce the phase shift. So phase shift says I'm going to move all this over. To the right. Okay, we got ourselves a little problem because I didn't even know where pi is. I got 2 pi over 3. So what I'm going to have to do, I'm going to have to keep on going until I get to, that's going to be 5 pi over 6. And then I'm going to eventually get to 6 pi over 6. There it is. There's my pi. We good? Still got to go find it. Now I'm going to have to bring it all the way back. So let's see, pi at 6 pi over 6, it's actually on top. So that means if I bring it all the way back over here, it's going to stay on top because I'm just going to subtract this out and get it all the way over here. So graph it, sort of made too many lines and dots here on the previous graph. So let me start here. This is going to be 2 pi over 3. 2 pi over 3, 2 pi over 2. Move it all the way back over here. So that means it had to be on top because it moves back this way. But that means the next one would have been down here. It matched up with this one. Alright, and then we can, once you get that, you can probably see the pattern as you go. Cool. Once you get 2 dots, you got it because you see the pattern. Okay, but notice what's happening here. Each time we have this little bracket, and any multiplier to the x is actually factored out. And then so it becomes a sort of clean phase shift. Because if it's there, then there's some other issues happening here. Alright, and the next one, it's not like that. Let's see if I have time here. I think so. Okay, so let me start it off here. Let me start off number 9A with you guys, and then you guys get the rest. B should be somewhat maybe easy. B is the toughie. B is the one that we have to sort of think through and maybe get a calculator out or something. We'll see how that works. Oh, you know, I'm so sorry. No, there's no graphing here. That's right. This is just give me the period, give me the phase shift. That's it. Alright, let me start off for you though. For A, notice it just has parentheses. I want a bracket and a parenthesis. I want to move that 2 out of there. So y equals 3 sine. Now it's going to be a bracket. Now the multiplier, I want to actually move away from the x. So it's going to be a multiplier of 2 moved away. I still have the x here. So anybody, what do you guys say for this? What should be in place of the pi over 4? What multiplies pi? What multiplies by 2 to get you pi over 4? So kind of just think about this here. If I were to multiply into here to get pi over 4, what would have to be here in order to multiply by 2 to get a pi over 4?
Something over 2.
Close the other way, the other way. How about something over 8, right? Because if you multiply by 2, it's going to reduce that 8 down to a 4.
Oh, okay.
All right, so what I need here, no graphing, no needed. Just give me period, give me phase shift. That's all I need. Period, phase shift. And for the other one as well.
Phase shift is pi over 8.
Almost. Let's go with period first. Period is, let's see this guy, so 2 pi over 2. The divisor, how about pi is for the period? And phase shift is, we're almost there. How about a negative pi over 8? And it's the opposite sign. Okay, next one. See if you guys can do this one here a little bit more tough. I think you guys can still handle it though. Alright, so how about this one here? Y is equal to cosine of pi x minus 1. Move the pi out. Leave the x inside a parenthesis, which is inside a bracket. And all yours here. Tell me what that 1 had to be. Actually, what the number had to be in order to make a 1 when multiplied by pi. I can sing Jeopardy. Can't be a 1 in here because if you multiply pi times x, you get pi x. Multiply pi times 1, you get pi. But I have a 1 here. So what would this number had to have been if I were to multiply by pi, and then I get a 1 at the end? Awesome, I like that. We'll go with 1 over pi. Right, that's pi times x. As the pi goes into here, the pi and this pi cancels off, leaving you just with a negative 1. So all yours to finish off. Give me period, phase shift. And here we go. Period is 2 pi divided by pi, which makes just a 2. This is cool. I'll show you just a second here. Phase shift is pi. So here's what I got. I got a period of 2. So if I put a 2 here and I got a 1 here, I know it's cosine. Therefore, I have something that looks like this. I go here, 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 and here, right? So maybe like if in terms of minutes or in terms of seconds, I have something that's moving down in a second, then comes back up in a second. And notice these guys are just real numbers, right? They're not pi, yeah. In fact, pi's are still a real number, but they don't have degrees in them, right? It's just a real number to another real number by having that little pi as a multiplier over the period, or divisor over the period, which I think that's kind of cool. So then at that point, then you can do number of days, you can do number of seconds, you can do electricity going back and forth, except electricity does that 60 times in a single second. So imagine how fast the period there is. It has to do that in order to have electricity coming out of those outlets that we have in our houses and in buildings. Okay, think you guys ready for the big one? Here it is. Let you guys try it by yourself. Can you graph this for me? And I think you guys know what -2 does at the end of something. I'll let you guys figure that one out, but to give you guys, try by yourself first. All yours, go for it. Because we put all the pieces together at this point. All right, remember it's a sine curve. Ooh, of course, the honesty question is raise your hand if you, because we knew we are going to be doing 5.4. Raise your hand if you actually read 5.4 prior to coming to class. Ooh, all right, a whole 2 people. All right. Now, how many sitting there wish you would have read 5.4 prior to coming to class? Okay, there you go. And that's something probably Ryan can help you with, right? So you're not all alone by yourself trying to figure things out. But I think he tries to preview the next sections with you guys. That's something somewhat important. All right, give you guys a minute here. Try it yourself. All right, let's go for it here. So first things first, let's make it so that there's brackets here as well. So I kind of switched them. Parentheses, brackets, brackets, parentheses. Doesn't matter too much. But 3 goes on the outside, so then the thing that's left over is just a pi over 9, true? Because you multiply. When you multiply this 3 times this, that's what gives you, or is going to give you that negative pi over 3. All right, -2 in the back still stays -2. Again, this is going to be going down 2 units at the end. But let's go for it here. So amplitude is 4, period is 2 pi over 3, and then the phase shift is a pi over 9. Right, we're going to move this guy to the right, pi over 9. All right, and then the new one here, which I think you guys should have figured out, is the VS, or we call it the vertical shift. We got a vertical shift of -2 at the end here. All right, let's see how we can set this up here. So period is 2 pi over 3. I'm going to have to sort of put this guy all the way over here to make a nice graph. Then I'm going to chunk it up into 4 different pieces, right? Because they all have quarters here. So half of 2 pi over 3 is a 2 pi. So pi over 3. And then half of that would be a pi over 6. So we start counting pi over 6, 2 pi over 6. 3 pi over 6 would be here. But let's go a little bit further in because we need that little pi over 9, right? Isn't pi over 9 about this big? Smaller than pi over 6. So that would be 2 pi over 9. Let's see if this makes sense. This is 3 pi over 9, is that right? 3 pi over 9. And the reason why I'm doing this is because of this right here. Because my period is in terms of a denominator of 3. But my phase shift is in terms of denominator of 9. So I pretty much have to make all these things in terms of a denominator of 9. Just so I could see the movement here. All right, how do we build this one here? What's the middle ground between pi over 3 and 2 pi over 3? You have to add it up, right? Is this 3 pi over 3? So just pi. Oh, divided by 2. So your pi divided by 2 because you're taking the middle of it. Okay, so 4 pi over 9 is right here then. 5 pi over 9 would be on this side of pi over 2. And 6 pi over 9, hey, that's the same thing as this one right here, right? 6 pi over 9. That's here. Alright, we can go to the negative side as well, but I think for now we're okay. Let's make this here, and I'll wait for you guys to catch up. Alright, so let's see. We have a sine curve on our hands, so that means I start off with 0. That's nice. My period is 2 pi over 3, so that means halfway through, quarter of the way through, it's going to be at 0.7. At pi over 3, it's going to go down to 0. Then halfway through here, it's going to hit a negative 4. And eventually get up to 0 at 2 pi over 3. Okay, those are my dots. I've taken care of amplitude because I raised it 4 instead of 1. And I've taken care of the period. I got the 2 pi over 3 and divided to 4 pieces. Alright, what I don't have yet is the phase shift and the vertical shift that I don't have. Alright, but let's go. Start off with 0, 0 because this is an important point. And we're moving pi over 9 to the right. So we take this dot here. We're going to move this guy over. And then we're going to move it down. Everybody okay with the dot here? Well, first of all, we can move it. We can slide all these dots over, right? Pi over 9 gets moved, pi over 9 gets moved, pi over 9, pi over 9. If you need to, you can also check by either using a calculator or check by adding them up. Like 4 pi over 9 plus, I'm sorry, 3 pi over 3 plus pi over 9 will get you 4 pi over 9. Pi over 2 plus pi over 9, doing some work there, will get you over here. And again, so on and so forth. Then we also have to move down 2 units. So down everything. This is one I'm sort of checking right here. If this makes sense. So 2/3 plus a pi over 9 would be somewhere over here. This guy is 7 pi over 9, where it hits the 0 again. Alright, and then we move everything down 2 units. So down on the green, down 2 units here, down 2 units here, down 2 units on the green, and then down 2 units here. Eventually, I can finally make myself a graph. Whew, that was cool. We went from nothing to graphing something like this in an hour and 30 minutes or so. Okay, where do we use this? I just want to show you at least a little something. Practice problem number 12 deals with something that it's from the textbook here, so I'm going to skip that one a little bit here. Let's go to just this something called simple harmonic motion. Simple harmonic motion just means things are going up and down, up and down. Things that do that, if you turn a grandfather clock sideways, that would do that too, right? It goes up. You can sort of, as long as it goes sideways, then you're fine. Let's see, what's another one? A wheel, not a wheel, but a tire on a car, tire on a bicycle. That has the motion, right? If you kept the point would just go up and down, so you have something like that. That's what it's meant by harmonic motion. Okay, so yes, we do need the amplitude. Yes, we do need the period, and we need the something called the frequency at this point. The frequency is the motion, omega divided by 2 pi, gives the number of cycles completed per a unit of time. So how fast it's climbing back up. Okay, I'm going to just look at an example, that's all. I don't think we have time to do one here, but suppose that a ball attached to a spring is pulled down 6 inches and released, resulting in a simple harmonic motion, has a period of 8 seconds. So it's pulled down, let go, and the spring, because it's very springy, it allows the ball to go up, but the ball has lots of mass as well, so then it goes down, then it goes up, then it goes down because of the spring. So it's sort of teeter-tottering here between the two. Write an equation for the ball's simple harmonic motion. Alright, so first we have to start off with the negative because the ball is being pulled down. We start tracking the ball, so notice it takes a period of 8 in order to get back up to it. So what we really want to do is we want to figure out what in the world is omega. And as we do that, we multiply both sides by omega, divided by 8, and we get omega to be pi over 4. So that has to come in for omega. That's the number that multiplies. And this time it's in terms of t because it's in terms of seconds. Let me just go back up real quickly here. Yeah, we chose a negative for the 8 because it was down on the bottom as opposed to a positive. And it was cosine is the best one to use at this point. What we normally do, whenever something is starting at a low position, we just use cosine for it because cosine is going to nicely show you. If we start at a high position, like we're throwing something down but then it's going to spring back up, we start at a high position because it's going to go to this. Sine curves tend to be at 0, and again that starts what happens if it's starting and it's just starting to stretch. And so we kind of use whatever value we need. Since we know we pulled it down 6 inches, we're trying to use that formula. So we're going to use a negative in front of cosine to bring it starting at a negative level. So all yours here. Rework number example 13 with this period of 3 seconds, and the ball is pulled down 4 inches and then released. So I'll let you guys struggle with that one just a little bit here. So pull down 4 inches, that means I have an amplitude of 4, but I start off with the bottom, on the bottom. So then what do you think my A value is going to be? Alright, everybody okay with the A value of -4? We're going to use cosine, but there's the period. The period is 2 pi divided by omega. Omega is the period. It's the time it takes for it to go all the way up and then come all the way down. In this case it says it's 3 seconds. So 3 pi over. So all we really want to get out of it is just the whole concept of what is omega. Omega is 3, and omega is the number that's multiplying the t in the front. So y is equal to -4 cosine of Okay, I go with it.